Welcome back to this channel. My name is Dr. Arzu Chabra, and I have a PhD in organic chemistry, and I'm also a mindset academic coach for college students. So today we are going to be working through the problems of carbohydrates, and these are the Kaplan problems that we are solving today. And of course, if you want to download these problems or like the PDF, if you want to solve these problems along with me or even separately and then come back here and double check your answers, feel free to download the video or download the PDF in the link mentioned down below. And let's get started. So when glucose is in a straight chain formation, it is a aldoketose, it is a pentose, has 5 chiral carbons, is one of 16 stereoisomers, right? So glucose is actually not an aldoketose, it is an aldose, right? It has the aldehyde part of it. It is a pentose, which is also incorrect because it actually is a hexose. Has 5 chiral carbons, which is also incorrect because it has 4 chiral carbons and is one of 16 stereoisomers. And so 2 raised to the power of 4 because it has 4 chiral carbons. So that would equal 16. So it does have 16 stereoisomers and glucose is one of them. So option D is actually the correct answer for this problem. Okay, all of the following are true of epimers, except they differ in configuration about only one carbon. They usually have, which is true. They usually have slightly different chemical and physical properties, which is also true. They are diastereomers, with the exception of glyceraldehyde. They are diastereomers. They always have equal but opposite optical activities, which is not true because that is only true for enantiomers. So, and then because they're diastereomers, option D is the correct answer over here. The above reaction is an example of one step in. Okay, so if we actually look at this reaction over here, what we really see here is that in the reaction of this aldehyde, right, we have in the ring formation, right, when this hemiacetal ring is being formed, we do really see that OH is pointing down and one of the other OH is pointing up. So what we do really see here is a muta rotation happening because the OH pointing in 2 different directions, right? That is actually called muta rotation, and that's exactly what is happening. And so it's not in aldehyde formation, it's actually hemiacetal formation, not really hemiketal, right? Because it's not a ketone, it's an aldehyde. And then we've got glycosidic bond cleavage. So it is also incorrect because it's not even a glycosidic bond over here. Okay, what is the product of the following reaction? So if we look at this reaction, right, what we really see here is that we have methanol reacting, right? So we have a methanol. It's reacting with this compound, which is actually a carbohydrate. So when the methanol is reacting with this carbohydrate, then that reaction, right, would actually be more of a, so we have an alcohol here. I see, right? So we do have an alcohol here, acidified alcohol, and everything else over here, let me look at all the other options. Yeah, right, everything else is an alcohol, and an alcohol. So we have learned that the reaction actually happens. There's a reaction of an aldehyde, right, with aldehyde with an alcohol. And what we know is that this this alcohol over here is actually more like a acetal, right? So if it is more like an acetal, it was actually prepared, or hemiacetal was actually prepared initially. It was an aldehyde before the ring closing happened over there, right? So we can actually say that it would have actually been that C double bond O over here. So an aldehyde, right? So an aldehyde and an alcohol reacts to actually form an acetal. So then we should actually get that acetal over here. And so that would give us option B. So okay, actually, so it was initially an aldehyde, right? An aldehyde reacted with this alcohol to actually form this hemiacetal, and now hemiacetal is reacting with alcohol to actually I should have been more specific here, right? So we really have hemiacetal here, and that is actually reacting with an alcohol to give us an acetal, correct? And a full acetal actually looks like this, the one which actually that oxygen will actually have the OCH3, right? So that would actually have the OCH3 over here. So then option B is the correct answer for this problem. Which of the following compound is not a monosaccharide? So if you actually think about it, deoxyribose is a sugar present in DNA. Fructose is also a monosaccharide, meaning one cycle chain of carbohydrate. And so is glucose. However, maltose is not. So option D is the correct answer. The cyclic forms of monosaccharides are hemiacetal, hemiketal, and acetal. So monosaccharides, right, when the C double bond O or the aldehyde is actually present at like the first carbon of that long chain or the Fisher projection of that monosaccharide, right, we actually form a hemiacetal. However, if it is something like fructose, so then the C double bond O is kind of, or the ketone is actually present at the second carbon, and then we have a CH2OH here. In that case, when the cyclic form is formed, right, then we actually form a hemiketal. However, acetal is never directly formed unless you add excess of methanol in the presence of acid. That will actually give you acetal. So 1 and 2 only are the correct answers. When the following straight chain Fisher projection is converted to a chair or ring formation, what would be its structure? Okay. So if you actually go about drawing out the structure, right? So we have a CHO. So what I like to do over here is tilt, make the molecule horizontal, right? So if I have CHO, so then I'll have HOH, OHH, and then HOH, HOH. So we have C, and then OHH, HOH, HOH, and then CH2OH. Okay, and so we then would have actually, if I close up the ring, right? Right. So if let's say this alcohol is actually attacking over here, right? So then I would have C. Something's wrong, right? Of course, something's wrong here. That oxygen is not the one that attacks. So let's say this oxygen will actually attack here, right? So, and because the ring is actually being formed from the top, so 1 second, we have CHO, OH, okay. So that attack is actually happening like this, right? And then in that case, then we would have COH and H, of course, that can go above and below, right? And then that would be this carbon. This for the second carbon, we have OH pointing down. The third carbon has OH pointing up. Down, up, okay. And then down, and then CH2OH. So option C looks like the correct answer for this problem, really, right? So if you think about it, this H and OH, so we really want the H to be pointing up, right? So we want the H pointing up, OH pointing down, OH pointing up, OH is pointing up, H is pointing down, H is pointing up, OH is pointing down, right? Then the next is CH2OH and the oxygen forming the cyclic structure. So then this is how just the ring is actually formed. Okay. What would be the product of the following reaction? So we actually have anhydride. CH3, CH2, C double bond O, and then oxygen and C double bond O, and CH2, CH3. Okay, and so we have all these different alcohols, and that is an ester already. So we have an ester in all these different alcohols. So all the alcohols can be converted to O, C double bond O, and then CH2, CH3. So then option C actually looks like the correct answer, right? Because then every alcohol can actually be converted to an ester, right? So every alcohol, when treated with anhydride, can go over here. This can go above, this can come back, and this can go over here. So we would actually get O, C, double bond O, CH2, and that's CH3 on every alcohol of the group. And so that would result in that ester formation. And that is option C for that answer. Okay, which of the following are reducing sugars? So we do know that fructose, galactose, glucose, they all have aldehydes present in them, right? Therefore, all of the above are actually reducing sugars. What description best fits the pair of sugars shown below? So for these sugars, we actually have One of the chiral center is the same. Second chiral center is also exactly the same. The third chiral center is actually, let's see if there's a difference in the stereochemistry really fast, right? So then this would be number 1. This would be 2. I'm just checking the stereochemistry really fast. 1, 2, 3, 4. Okay, so 1, 2, 3. I'm going anti-clockwise. Anti-clockwise is S. However, the least priority is on the horizontal bond. And so if it is on the horizontal bond, it is S on the horizontal, which makes sense. So that is S. Now, for the other ones, we've got 1 CH double bond O. Aldehyde is number 3, and that is number 4. Actually, ideally, I think the least substituent should be on the vertical bond and not on the horizontal bond, right? So the rule is that when the fourth priority is on the vertical bond, so it would actually be R over here. Okay, and now if we go 1, 2, 3, 4. So we are going clockwise. It should be, so that is R as well. So they actually are identical, right? Because there's not really a difference in the stereochemistry of the last one. So they are the same as well. And if you check, they are double inversions. Of that, we will talk about that later. Okay, galactose is a C4 epimer of glucose. And if you actually think about it, for this problem, we have 1, 2, 1, 2, 3, 4, 5, 6. Okay, and then we have 1, 2, 3, 4, 5, 6. And then we have 1, 2, 3, 4, 5, 6. Okay, add the C4 carbon. Let's really fast check the stereochemistry. We have stereochemistry for C4OH pointing on the right, C4OH pointing on the right, right? C4 pointing on the right. And then for C4OH is pointing on the left. And over here, OH is pointing on the right again. So of course, we can only have one correct answer for all of those at C4. The stereochemistry is just pointing on the right. However, of course, we can only have one correct answer, which would be different. So option A is the correct answer for that problem. Okay. I have to run to a class right now really fast. Let me see if my student is here. Okay. So really fast, let me finish off this video. Under strongly acidic conditions, aldoses become oxidized to dicarboxylic acids called aldaric acid. An unknown pentose X, which is optically active, produces an optically inactive aldaric acid upon treatment with HNO3. What is the structure of pentose X? Okay. So what they're really saying is that they start off with optically active and end with optically inactive, right? So how that's only possible, and of course they're oxidizing it, meaning the top one is converting to C double bond OOH, the bottom one is converting to C double bond OOH. And then we have HOH, and then we have HOH and OHH. OHH, HOH. Okay, so all we have got to figure out which of these after oxidation will become optically inactive, right? Because if they're optically inactive, then, or if they're symmetrical, then they're optically inactive. So if you look at option D here, we would have C double bond OOH, then we would have C double bond OOH, and then at this plane of symmetry, the molecule is optically inactive. So this option D is the correct answer for this problem. Okay, so with that, we've come to the end of this chapter. I think I have amino acid left over from Kaplan, and which is, so I've got amino acid, peptides, and proteins. And I've got spectroscopy. I'm not 100% sure if I would actually be solving spectroscopy problems, but right after I finish the amino acids, I'll definitely jump into solving like full-size practice problems from the organic sections, and maybe I'll include a little bit of the chemistry sections as well. And until then, keep learning, keep growing. And for all the details on our mindset classes happening on Sundays, check out the details down below. And I will see you guys later. If you're interested in any kind of tutoring or coaching, feel free to reach out, and we'll see you guys later. Bye now.